and both Paper 1, Physical and Inorganic, and Paper 2, Organic, focusing on topics that frequently appear and require precise, structured answers to maximize marks. Paper 1, Physical and Inorganic Chemistry. Question 1. Coordination Chemistry. 10 marks. Q. Explain the structural and electronic factors that cause the Wacker process to be highly selective for the oxidation of ethene to acetaldehyde. Discuss the role of palladium-2 and copper-2. Answer. The Wacker process is a classic example of homogeneous catalysis involving a palladium alkene complex. The high selectivity relies on a precise sequence of organometallic steps. 1. Pi complex formation, palladium. 2. Tetrachloropalladate, PDCl_4, caret 2, undergoes nucleophilic substitution where an ethene molecule replaces a chloride ion to form a pi complex. PDCl_3, eta squared text, C_2, H_4, caret 2, nucleophilic attack, hydropalladation. A water molecule attacks the coordinated ethene. This is a crucial regioselective step, converting the pi complex into a sigma-bonded beta-hydroxyethyl palladium intermediate. 3. Beta hydride elimination and insertion. A series of internal rearrangements, beta hydride elimination followed by reinsertion into the PD text H bond, shifts the hydroxyl oxygen to the terminal position, ultimately yielding acetaldehyde and regenerating PD0 and HCl. Role of co-catalysts. Palladium, 2. Acts as the primary catalyst that activates the alkene toward nucleophilic attack by water. However, it gets reduced to metallic PD0 in the process, which terminates the reaction if left alone. Copper, 2. Acts as an oxidizing agent to regenerate PD2 from PD0. Oxygen, O_2. Air or molecular oxygen is used to reoxidize the reduced copper-1 iodide back to Cu2, making the overall process catalytic with respect to both metals. Question 2. Chemical thermodynamics. 15 marks. Q. Derive the Clausius-Clapeyron equation for a liquid-vapor phase equilibrium. State the key assumptions made during the derivation. Answer. For any two phases, alpha and beta, in equilibrium at constant temperature and pressure, the chemical potentials of the two phases must be equal. For an infinitesimal change along the phase boundary, using the fundamental thermodynamic relation dG equals VdP SdT, rearranging gives the Clapeyron equation, where delta H is the enthalpy of the phase transition and delta 5 is the volume change. Transition to Clausius-Clapeyron, liquid to vapor. To apply this specifically to a liquid-vapor transition, delta H equals delta H_vap app, we introduce two major assumptions. 1. Assumption 1. The molar volume of the gas, V_G, is vastly larger than the molar volume of the liquid, V_L. Therefore, the liquid volume can be neglected. 2. Assumption 2. The vapor behaves like an ideal gas. Therefore, we can substitute V_G equals frac RTP into the equation. Substituting these assumptions back into the Clapeyron equation, integrating this expression, assuming delta H_vap is constant over the temperature range, yields the standard integrated form. Paper 2, Organic Chemistry. Question 3, Reaction Mechanisms. 20 marks. Q. Distinguish between the benzene, elimination-addition mechanism, and the S_NAR, addition-elimination mechanism for nucleophilic aromatic substitution. Provide experimental evidence supporting the existence of a benzene intermediate. Answer. The two mechanisms differ fundamentally in the sequence of steps and the nature of the intermediates involved. Feature. _NAR, addition-elimination. Benzene, elimination-addition. Substrate requirement. Requires strong electron withdrawing groups, like NO_2, ortho or para to the leaving group. Occurs on aryl halides, lacking activating groups, usually requiring very strong bases, e.g. NaNH_2. Sequence. 1. Addition of nucleophile. 2. Elimination of leaving group. 1. Elimination of HX to form an alkyne. 2. Addition of nucleophile. Intermediate. Meisenheimer complex. Carbanion stabilized by resonance. Benzyne, arine, containing a highly strained formal triple bond. Regiochemistry. Ipso substitution only. Nucleophile attaches precisely where the leaving group was. Cine substitution observed. Nucleophile can attach to the leaving group carbon or the adjacent carbon. Experimental evidence for the benzyne intermediate. 1. Isotopic labeling. Cine substitution evidence. When chlorobenzene labeled with Cary14C at the C1 position is treated with KNH_2 in liquid ammonia, the resulting aniline consists of an almost equal 50-50 mixture of C1 labeled aniline and C2 labeled aniline. This proves that the symmetry of the intermediate allows the nucleophile NH_2 to attack either carbon of the triple bond with equal probability. 2. Diels-Alder trapping experiments. Benzyne is a highly reactive dienophile due to the strain of the triple bond in a 6-membered ring. The orbital overlap occurs in the plane of the ring using sp² orbitals rather than normal unhybridized p orbitals. If generated in the presence of a conjugated diene, like furan or anthracene, it immediately undergoes a 4+2 cycloaddition to form a stable adduct, e.g., endoxanthracene with furan, proving its fleeting existence in solution. Key tips for writing chemistry optional answers. Mechanism arrows. Always draw clear, unambiguous curved arrows showing electron flow from nucleophile/bond to electrophile. Thermodynamic conventions. Pay strict attention to IUPAC sign conventions, e.g., W equals delta 5 for work done by gas expansion, to avoid dropping marks on physical chemistry derivations. Structure. Divide your answers with clear headings like mechanism, assumptions, and experimental evidence to match the valuation criteria of the examiners.